There are a couple of examples in the book that are really good, so I printed them here for you guys because I think it's a good couple of integrals to get started with. When you're using U-substitution, what you're trying to do is find a U and a du that goes with it. Okay? And the du is going to have the dx part, right, with it on the right-hand side. So in this case, what do you suspect u should be? Cosine x, yes. So we'll let u equal cosine x. And du here is a negative sine x dx. But I do not have a negative in there in the integram, so I'm going to bring the negative out in front. Negative du equals sine x dx. So replacing my variables, I'm going to put a negative in front and then get e to the u du, which everyone likes to integrate, I hope. And that's just e to the u, negative e du, plus c. And u is cosine x. So then we can say the antiderivative of this is negative e to the cosine x plus c. Okay? Moving right along. Oh, there's one on the same page, right? Sorry about that. Nope, I made it a different document. Okay. Ordinarily with U-substitution, would you choose for u what you're raising to a power. Okay, but this one we've got two things being raised to a power. But you see a function and maybe part of its derivative. That's a yes or no. Probably going to help if I have some audio. So I would let u here equal 5 plus 2x to the third. Good. And then du is going to be 6x squared dx. Now I'm happy to see this because if I were to solve for x squared dx, which I have in my integrand up here, this would be du over 6. So it's just a constant difference there. And so I'm going to bring the 1/6 out in front, change my variables, and so this is now u to the 1/2 du, and we can use the power rule here. So that's going to equal 1/6. We raise the power 1, u to the 3/2, multiply by 2/3, plus the cupcake there. And we could reduce. 2 goes into 6 3 times, right? And so what is u? U is 5 plus 2x cubed. So this would be 5 plus, 5 plus 2x cubed raised to the 3/2 divided by 9 plus c. Okay? Next one. Those ones are two pretty simple examples. All right, on this one, got to get a little bit more creative. What do you see a function and its possible derivative? So what are we going to let u be? ln x. Good, because du, the derivative of ln x is 1 over x dx. And I do have the 1 over x in here, even though it might not look like it. And so this is going to be the integral of 1 over, am I delayed? 1 over, 1 over the square root of 1 minus u squared du. Whose derivative is that? Inverse sine of u. But what is u? That's what we said u was. All right, next one. Sometimes trig identities can help because cotangent doesn't have a straight up antiderivative. It's not one we know. So we can change the cotangent into its sine and cosine component parts, right? And we can let this be, what is cotangent? Cosine of 7x over sine of 7x dx. Now, just like we usually choose things that we are raising to a power, normally we'll choose the denominator for u. So let's try it. So u equals sine of 7x, du equals cosine of 7x times 7 dx. But what do I have in my integrand? I only have the cosine x, 7x dx. So I have to divide by 7. So I'm going to bring the 1/7 out in front, integral of, now this is 1 over u du, whose derivative is 1 over u? So 1/7, the natural log of the absolute value of u plus c. So our integral is going to equal 1/7 natural log of the absolute value of sine of 7x plus c. So the strategy to integrating cotangent is bust it up into its cosine over sine parts. Sometimes there's a nice integral in disguise. Well, this one is not particularly nice. If I were to let u equal cosine 2x, do I have the du associated with that, which would be negative sine x dx times sine 2x, I'm sorry, try again, negative sine 2x times 2 dx. Is that anywhere in the integrand? Nope, so I'm in trouble. But what is 1 over cosine squared? Secant squared. So you can rewrite this as secant squared 2x dx. And whose derivative is secant squared? Tangent, right? So this is going to be tangent of 2x over 2 plus c. Now, I could have used U-substitution here, but I'm hoping you guys are going to get to the point with trig functions where if I have secant squared kx or tan x secant x, when I have a constant in here, instead of multiplying like we would with when we take a derivative, you divide by the inside constant. Okay, so this would be tan kx over k plus c. Okay, and like e to the 2x would be e to the 2x, the antiderivative e to the 2x over 2 plus c. All right, you have to be pretty quick at that, but that would be the answer to that one. So it was a nice one in disguise. What about cotangent squared? 3x. If I went cosine squared 3x over sine squared 3x, I have a square in the top and a square in the bottom, so that won't work. So we have to use an identity here. Do we know what cotangent squared equals? Integrate cotangent. You're going to say cosecant squared 3x minus 1 dx. You got to use the Pythagorean identity for that. Now, why would I want to use a Pythagorean identity for that? Because do we know the antiderivative of cosecant squared? Yeah, we do, don't we? It's cotangent. So can we decide that this is going to be negative cotangent of 3x divided by 3 minus yes, x, good. So the strategy to integrating cotangent squared x is to change it to cosecant squared x minus 1, because we know the antiderivative of cosecant squared. Okay. What about cosine cubed? If we were to let u equal cosine x, what's du? Negative sine x dx. Do I have a sine x dx in my integrand? No. Is there a way to bust this up where I might? You could rewrite this as the integral of cosine x times cosine squared x dx. Is there a way to get a sine in there now? That's right. We can say that this is cosine x times 1 minus sine squared x dx. Now, if we let u equal sine x, what's du? If I let u equal sine x, u equals sine x, du equals cosine x dx. Do I have that in the integrand? Yes, right, here's my du. So you can say then that this is going to be the integral of 1 minus u squared du. Now watch it here, because we're integrating now with respect to what? U. So when I take the antiderivative, I'm going to have u's, not x's, okay? So then what happens here? I say the antiderivative of 1 is u, good, u minus, yep, 1/3 u cubed, plus c, but what did we choose for u? Sine. So this is equal to sine x minus sine cubed x over 3 plus c. All right, so if you have a, like, sine to the 5th, what do you have to do? You bust it up, right? So we can get a cosine in the integrand somewhere. Okay. Sometimes the simpler trig identities are not enough. And we need to reduce the power somehow. Now, you can't blame it on your pre-cal teacher that they didn't teach you the power reducing identities, because guess what? She's standing right here. Or you could try. But let's pretend we forgot what they were. Okay?
Just pretend.
I know what they are.
Maybe it's not pretending, right? Okay, here we go. Cosine 2x. Oops. Anybody remember what the identity is for cosine of 2x?
Cosine squared minus sine squared.
Sorry?
Cosine squared minus sine squared.
Okay, cosine squared x minus sine squared x, right? Now, I taught you the all cosine version and the all sine version, right? Now, I don't expect you to necessarily memorize that, but okay, which do I need here? What do I need this equal to? Sine squared. So I need to eliminate the cosine squared. So I'm going to make this cosine 2x equals 1 minus sine squared x minus sine squared x equals 1 minus 2 sine squared x equals cosine 2x. And now I'm going to solve for sine squared x. So I'm going to add the 2 sine squared x to this side, and then move the cosine over, and then divide by 2. But I'm going to leave the 1/2 on the outside, right, because it's a constant, correct? just found out here, right? Or rediscovered, shall I say, yes? So I'm going to put the 1/2 out in front times the integral of 1 minus cosine 2x dx. And now what we've done is reduced the power on the sine squared, and now it's just a cosine that's not squared, which we know how to find the antiderivative of. Okay? The only way to integrate sine squared x is to use the power reducing identity. Okay, so let's do this. This is going to be 1/2 times the antiderivative of 1x minus the antiderivative of cosine 2x. Sine 2x over 2. Good. Plus c. There it is. I would memorize it now because in Calc 3, you integrate a lot of sine squareds and cosine squareds. What?
What is Calc 3?
3D space, where you have triple integrals. These are single integrals.
What major should I major into?
Why would you want to avoid that? That's when all the cool stuff happens. Oh, you can still get an A, even though you don't believe it. Okay, cosine squared x. What do you suppose we have to do? Power reducing. Now the power reducing for cosine is the same as sine, except it's plus. Do you need me to derive it, or?
I take your word.
Okay, so, thank you. Cosine squared x is going to equal 1/2 times 1 plus cosine 2x. Yes. Now, how do I remember this? Sine begins with an S, and it's subtraction. That's how I remember it. All right, so we're going to replace this cosine squared x with 1/2 the integral of 1 plus cosine 2x dx. So the antiderivative of 1x, antiderivative of cosine 2x is sine 2x over 2 plus c. Alright. So now you know how to integrate. More and more stuff. Here we go, moving right along. Ooh, sometimes you wish the constant was a 1 instead of a 16. Boy, if that 16 was a 1, what would this be? Inverse tangent of x, right? Well, there's a technique we have to use to make that 16 into a 1. What? Whiteout? Yes. Yes, whiteout might work. It would definitely be more challenging to do it my way. Very good. All right. Sadly, we got to use some calculus whiteout. All right, so what we are aiming to do here is to factor out that 16, okay? So I'm going to set up a U-substitution. I'm going to let U, or let me rephrase that. I'm going to let 4U equals x, equal x. Because what happens when I square that? You get 16U squared equals x squared, right? So far in the integrand, what have I replaced? This is 16 plus 16U squared, but now I have to replace the dx. So I need to take the derivative of this. What is the derivative of 4u? 4 du equals dx. So wherever I see the dx, I'm going to put a 4 du. I'm going to bring this out in front. Okay, now, what can I factor out of the bottom? 16. So if I factor over 16, I get 4 over 16, which is 1/4 times the integral of 1 over 1 plus u squared du. And aren't you happier about that? Yes? Because what is this integral? This integral is 1/4 inverse tangent of u plus c. But what is u? Now watch it here. X over 4, right? Because you have to divide this. So it's 1/4 inverse tangent of x over 4 plus c. Okay? I have one of these on every all or nothing.
Yeah. It's like a linguistic difference.
Right?
It's just the weird thing.
Okay, this is a subtly different version of this. Oh, I wish that 9 was a 1. So what do you, oh yeah, Mitchell, you're right. So we're going to let 3u equal x, because what happens? We get 9u squared equals x squared, and if I take the derivative of this, I get 3 du equals dx. And what do I bring out in front? A 3, and then I'm 1 over the square root of 9 minus 9u squared du. And now, under the radical, I can factor out a 9, right? So I get 9 minus 1, 9 times, excuse me. 9 times 1 minus u squared, right, du. Now I'm happy because the 1 has arrived on the scene. Now what is the square root of 9? 3, so the 3's cancel, and I'm left with the integral of 1 over the square root of 1 minus u squared du, which is inverse sine. This is equal to the inverse sine of u plus c, but what is u? U is x over 3. Inverse sine of x over 3 plus c. So I've given you the inverse tangent version and the inverse sine version. Okay? Of the oh, I wish it were a 1.
Oh wait, there's more.
Is there more on the page?
No, like this.
Oh yes, there's more. Yes, sometimes you need to multiply by a seemingly bizarre factor of 1. Yes, this is the one I foreshadowed earlier, you know. This you have to multiply by a factor of 1 that might seem nonsensical to you, but it actually works because you're creating a u and a du. And so you multiply this by secant x plus tan x over secant x plus tan x. And that what happens when you do that to the numerator, you get secant squared x plus secant x tan x, which these two characters up here in the numerator look like derivatives of some things that we know. And then we get secant x on the bottom plus tan x du. And so the numerator looks like whose derivatives? Tangent and secant, which happens to be on the bottom. So we're going to let u equal secant x plus tan x. And du will be secant x tan x. It doesn't matter which order, right? Because it's addition, and addition is commutative. Plus secant squared x, all times dx. So then all of this mess turns into something really nice, 1 over u du. Whose antiderivative is ln of absolute value of u plus c. And u is natural log of the absolute value of secant x plus tan x plus c. My magic ink. That's the only way you can integrate secant x. Was I born knowing that? No. I stood on the shoulders of somebody that learned it before me, and right? All right. Cosecant is similar. What am I going to multiply that by? Cosecant x plus cotan x. It has to be over 1 because I don't want to change the integral's value. I just want to change the way it looks. Okay. So on top then we're going to get cosecant squared x plus cosecant x cotan x all over cosecant x plus cotan x dx. So what do you suggest we use for u? Yep, the denominator, so we'll let u equal cosecant x plus cotangent x. Du will be, now watch it, these are both negative, aren't they? So I'm going to say this is negative cosecant x cotan x minus cosecant squared x all times dx. But do I have the negative in the numerator? Nope. So I'm going to divide by the negative and make this positive. And then I can complete my U-Substitution. This is the dx, I'm sorry, at the end. And so negative on the outside, this turns into 1 over u du, except that it's negative. So the antiderivative is going to be, good, negative natural log of the absolute value of cosecant, I'm going to put u first, sorry, u plus c, and it turns out to be negative natural log of the absolute value of cosecant x plus cotangent x plus c. So, that seemingly bizarre factor of 1 is the only way to integrate secant x and cosecant x. Some integral U-subs are just downright complicated. Now some of you guys were having great trouble with tangent to the 4th, but now we have secant to the 4th. So we're going to have to use an identity because secant's derivative is secant tan, right? But if I bust this up into secant squared times secant squared, can I change that and get a tangent in there somewhere? Yes. So, but I wouldn't change both of them, right? So the first step should be, let's change this into secant squared x times secant squared x. And then we'll change one of them into the identity. And what's the identity for secant squared? 1 plus tangent squared x dx. This one's actually not too bad. This one's easier than I think the tangent one that we were working on before after school. Okay, so we're going to let u, do you see somebody's derivative first of all? Whose derivative do you see? Tan, so that's what I'm going to let u be. U equals tan x. Du is secant squared x dx. And so I can rewrite this as the integral of 1 plus u squared du. See how much better this one is than the tangent before? Antiderivative here. Yes, u plus u cubed over 3 plus c, and u is tangent, so this is going to be tan x plus tan cubed x over 3 plus c. All right. Sometimes a little factoring would help us. suggestions? Difference of squares. So we could rewrite this as cosine squared x plus sine squared x. Oh, what's that? 1. Something wonderful just happened. Cosine squared x.
Wonderful.
Wonderful. Like really wonderful. Yes. And then something else, maybe not quite as wonderful just happened. What? Yes, this is what? Cosine 2x. Woohoo! And this is 1. So as scary as that was, it turned out to be something very simple, which is antiderivative of cosine is sine. So this is sine 2x over 2 plus c. So that scary thing turned out to be just the antiderivative of cosine 2x. So it's good to know your identities. It helps you. Moving right along. And sometimes you can celebrate. Celebrate good times. Come on. Now, why do we want to celebrate? What? Because x, we could make this go into all of them. So we can say that this is x squared over x plus 2x over x plus ln x over x dx. All right? So then that's going to simplify to x plus 2 plus natural log of x over x dx. All right, so let's do some integrating. What do we get here? X squared over 2 plus 2x. Now, this we're going to have to use U-sub here. You see a function and its derivative here? We could let u equal what? ln x, good. du is 1 over x dx. So this turns out to be the integral of u du, which is u squared over 2, right? So I can say that this is going to be plus natural log squared of x over 2. Now you do natural logs when you square them, just like you do sine and cosine and tangent and cotangent functions. You put the s in the middle between the n and the x plus c. So did you notice how I did a little U-sub in the middle of another problem? That's okay. Or long division can save the day. Now, I chose this one on purpose because this has got a irreducible quadratic factor in the denominator, right? So we can't use synthetic, right? I just wanted to remind ourselves that we can use, right, long division. So that's going to be x squared plus 0x plus 1, right? Because you have to have a placeholder for the x position. Divided into x cubed minus 3x squared plus 2x minus 3. And so we have to figure out what do I have to multiply times the x squared here to get x cubed? And it's x, so I'm going to put an x right here. And then I take this x and I multiply times everything here on the left, and I get x cubed plus 0x plus x. But I am subtracting. And so we get x cubed minus x cubed, which is 0. Negative 3x squared minus 0. So this is negative 3x squared minus x. Because this is what? Oh, plus x. You're right. I'm sorry. I am subtracting x, right? Yeah, 2x minus x is x. You're right. And then I have 3 terms on the. This is the divisor, right? Divisor. And I can bring down the negative 3. So I have 3 terms. Then I multiply this x squared on the outside here by negative 3. And then I get negative 3x squared plus 0x minus 3. But I am subtracting. And the first two cancel out. And then I get x minus 0x. So I get x. 3 plus 3 is, negative 3 plus 3 is 0. So this is going to be a plus x over what? X squared plus 1. So this integral is really looking like x minus 3 plus x over x squared plus 1 dx. And this is going to require two simple integrations here, and then it's going to require another U-sub. Okay, so I'm going to bring this down here. Integral of x minus 3 plus x over x squared plus 1 dx. So let's do the first two. Those are easy enough to do. X squared over 2 minus 3x plus, now this one's going to take a little bit of work. Why do I suspect U-substitution here? Do I see somebody's derivative up here? Whose derivative is that? X squared plus 1 actually, right? So we can let u equal x squared plus 1. Du equals 2x dx, which I don't have the 2. So this would be du over 2 equals x dx. Substituting in, I'm going to get plus 1/2 the integral. Good, 1 over u du, which we're getting used to being natural log. So I'm going to simplify my, this x squared over 2 minus 3x plus 1/2 the natural log of u, but u is x squared plus 1 plus c. Yes, sir.